Hi, Assalamualaikum. So today I would like to talk about the introduction for RFID. So, as you know, modern wireless technologies have transformed the way information is transmitted and exchanged in everyday life. Among these technologies, radio frequency identification has become an important system for automatic identification and tracking in various sectors. Conventional identification methods such as barcode system require direct contact or line of sight scanning and may be less efficient when handling large amounts of data. Therefore, RFID utilize radio frequency signals to enable a wireless communication between tag and readers without physical contact. This allows information to be transmitted, collected, and processed automatically in real time, improving the speed and accuracy of identification process. As a result, technology has been widely adopted in inventory management, healthcare, transportation, access control, and Internet of Things application, highlighting its significance in modern tracking and identification system, according to HiBy ETAL 2022. Hi, for this slide, I would like to talk about what are radio waves. So, radio waves are a type of electromagnetic wave that propagates through the environment and enables wireless transmission of information between devices. Unlike wired communication system, radio wave can travel through air and space without requiring a physical connection, making them highly suitable for long-distance communication. Furthermore, radio waves are invisible and inaudible to human, yet they are widely used in communication technologies such as Wi-Fi, Bluetooth, satellite communication, and RFID systems. They can carry information in the form of signal between transmitting and receiving devices, allowing data to exchange efficiently. As a result, radio waves have become a fundamental component of modern wireless communication network and play a crucial role in connecting devices in today's digital world, according to Otero 2025.
Let's look at the core component that make RFID system works. Think of this as a wireless barcode system, but without needing a direct line of sight. First, we must have RFID tag, which is attached to the item we want to track. Inside every tag, there is microchip to store unique identification data and an antenna to transmit the data. Next is RFID reader. This acts as a transceiver. It constantly sends out radio waves to find tags and receive the data then send as. Finally, we have the database. Once the reader captures the digital info from a tag, it transmits it to this backend system, which stores, updates, and processes the information for our software to use. So how it works? If you look at the system diagram on slide, the workflow is seamless. 1. The reader sends an interrogation signal via radio wave. 2. The tag enters the zone, catch the signal, and sends back a modulated cascade signal containing its ID. And 3. The reader converts this into a digital data and push it into the database. This entire loop happening wirelessly, automatically, and in milliseconds.
How RFID works? RFID reader emits radio waves. The RFID tag receives the signal. Then the tag says it stores information back to the reader. The reader transfers the data to a database for identification. Compared to the barcodes, RFID does not require a direct line of sight between tag and the reader. RFID technology is used in stores and logistic operations to provide quick and accurate data collection.
Okay, now let's explore the electromagnetic wave interaction in RFID system, especially on how radio wave enable communication between the reader and the tag. The working principle involves 5 key steps. First, the reader emits radio wave. The RFID reader generates electromagnetic wave at a specific frequency, either LF low frequency, HF high frequency, or UHF ultra high frequency. This wave propagates through the space. Second, the tag receives a signal. When the tag's antenna captures this radio wave, it converts the electromagnetic energy into electrical power. Third, the tag responds with stored information. Using the harvested energy, the tag's microchip modulates and backscatters the signal, sending back its unique identification data. Fourth, the reader receives the response. The reader's antenna detects the reflected electromagnetic waves that are now carrying the encoded tag information. And finally, the fifth, the data is processed by a computer. The reader decodes the backscattered signal and transmits the information into the backend database for processing and storage. As you can see in the visual, this creates a two-way communication flow. The reader sends an interrogation signal via radio wave to the tag, and the tag sends the data response back to the backscattered wave, all without any physical contact.
Now that we've seen how RFID works, let's look at one of the most important aspects that determines its performance, which is the frequency bands. RFID doesn't rely on a single frequency. Instead, it uses several bands, and each one has its own strengths and limitations. The choice of frequency determines how far text can be read, how fast data is transferred, and whether signals can pass through materials like water or metal. Let's look at the main bands and how they differ. Firstly is LF, which stands for low frequency. This band works at very low frequencies. Because of its long wavelength, it can penetrate water and metal better than higher bands. But it is low and only supports very short ranges. That is why it is used in things like livestock tags or building access cards. Next one is HF, which means high frequency. This band operates at 13.56 MHz. It is the band behind NFC that stands for Near Field Communication, which is used in contactless payments and library cards. It is faster than LF and supports more data, but the range is still limited to about 1 meter. Thirdly, UHF, also known as ultra-high frequency. It is the most widely used band for RFID today. It offers long read ranges up to 10 meters and fast data transfer, making it perfect for supply chain management and retail inventory. However, UHF signals do not pass through liquids or metals easily, and the exact frequency range differs by region, for example, the United States versus the Europe. Lastly is microwave. Microwave operates at very high frequencies, which is between 2.45 GHz and 5.8 GHz. This band allows very fast communication and long ranges, but it is costly and sensitive to interference. Microwave is used in specialized systems like toll collection, industrial automation, and medical applications.
Moving to real-world applications, RFID efficiency depends entirely on wave propagation. First, highway tolls use ultra-high frequency beams. Because these waves travel at the speed of light, they can power and read a moving vehicle stack instantly. Second, healthcare tracking monitors hospital equipment. The challenge here is interference. Because radio waves scatter, reader power must be precisely calibrated to avoid disrupting nearby medical instruments.
RFID has many advantages. It can scan information quickly without physical contact and can read multiple tags at the same time. It also helps improve tracking accuracy. RFID also has some limitations. The system is more expensive than barcodes, and signals can be affected by metal or water. In addition, the reader range is limited, and there may be security concerns if the data is not properly protected.
First, the future is all about combining RFID with the Internet of Things to create smart RFID IoT networks. This shifts us from basic scanning into automated sensing, allowing machinery, physical processes, and the environment to connect and share real-time data completely on their own. Second, expanding these networks means facing major technical complexities and security risks. Unpredictable environments cause signal instability, and open wireless channels leave data vulnerable. To fix this, the future of RFID relies heavily on integrating AI and blockchain to secure the data and handle those environmental complexities.
To wrap up our presentation, it all comes back to the invisible backbone of this technology, which is radio wave. As we've seen, radio waves are the fundamental medium that enable RFID system to communicate wirelessly. Without them, RFID technology simply couldn't function, as they are completely eliminate the need for a direct line of signs to capture data. But beyond just hardware, this wireless communication is what thrives efficiently in the modern global industry, because radio wave can pass through cardboard, plastic, and fabrics that allow businesses to scan hundreds of items simultaneously. This drastically reduces human error and accelerate processing times in everything from retail inventory to global supply chain and contactless payment. Ultimately, RFID isn't just about tracking boxes. It's a foundational pillar of the future of the Internet of Things. By seamlessly bridging physical objects with digital databases via radio frequencies, RFID will continue to shape the ultimate hyper-connected world of tomorrow. So that's it from us. Thank you.